Hello and welcome. In the deeper parts of the ocean, light becomes limited and movement slows. As depth increases, the surrounding water grows colder and more still. The following information moves gradually downward through these regions, describing how conditions change and how life continues within them. The sun's energy penetrates down into the upper portions of the ocean, where it drives nearly all of the photosynthetic activity that takes place. These illuminated zones receive incoming radiation that acts as the principal energy source for marine ecosystems, allowing microscopic phytoplankton to carry out the transformation of light into chemical energy that can be stored. The biochemical pathways involved in this process are well understood and have been studied extensively. This fundamental activity serves as the foundation for the entire food chain found throughout the ocean and makes a significant contribution to oxygen production on a global scale through the ongoing exchange that occurs during photosynthesis. The layer at the surface maintains continuous contact with the atmosphere overhead, creating conditions that permit heat and gases such as oxygen and carbon dioxide to transfer freely back and forth between the air and the water below. Winds that blow steadily across the ocean surface generate gentle mixing effects that help spread nutrients throughout the area and keep environmental conditions relatively uniform across extensive stretches of the upper ocean. The depth to which useful light can travel is influenced by several factors, including how clear the water is, the angle at which sunlight strikes the surface, and the seasonal variations that occur throughout the year. Despite these variables, the majority of productive photosynthetic activity remains concentrated within the brightly illuminated zone near the surface. This continuous influx of solar energy establishes a dependable pattern in which light intensity gradually becomes dimmer as depth increases, while biological activity and productivity remain concentrated in the layers closer to the surface. Once you descend to depths in the vicinity of 50 meters, you begin to notice that the light starts to weaken noticeably, and the colors that were visible higher up begin to fade away. Sunlight traveling downward through the sea water encounters a filtering effect where the longer wavelengths, such as red and orange, are absorbed relatively early in the descent, which leaves primarily the blue tones to continue traveling deeper into the water column. This progressive filtering reduces the sharpness of visual details and alters the way suspended particles and drifting creatures appear to an observer within the water. what remains of the light becomes increasingly scattered in all directions, spreading out in an even manner rather than arriving as direct, focused rays from above. The physical conditions at this depth are notably calmer compared to what you would experience right at the surface, though slow-moving currents continue to transport nutrients and microscopic organisms from one mass of water to another. The distance one can see clearly varies depending on the concentration of plankton present and the amount of dissolved materials in the water, but the overall pattern that emerges is one of steady dimming as you move progressively deeper. This transitional zone marks the beginning of a descent into environments where visual light starts to become less critical for the survival and behavior of many marine creatures. Surface waters receive their warmth primarily through direct exposure to the rays of the sun. The constant presence of sunlight enables the upper portions, organs of the ocean, to absorb and retain heat energy, which produces temperatures that vary according to latitude, the time of year, and the prevailing local weather conditions. Mixing driven by wind action helps spread this accumulated warmth throughout what is known as the mixed layer, which prevents the development of sharp temperature changes within the upper tens of meters of the water column. The ongoing contact with the atmosphere also plays a role in shaping temperature through processes such as evaporation, the addition of rainfall, and the exchange of heat that occurs during shifts in atmospheric conditions. Throughout many regions of the ocean, this warmer layer sits in a distinct manner above the cooler water that lies beneath it, creating a gradual temperature gradient that scientists refer to as the thermocline. The location where this gradient appears and the depth to which it extends can vary considerably from one ocean to another, but it consistently demonstrates the way the sun's heating power diminishes as you move deeper. These patterns of temperature distribution have important effects on water density, the patterns of water movement, and the way dissolved gases are distributed throughout the water column, all of which help maintain a stable separation between the upper zones and the deeper regions below. As you continue moving farther down below the surface, you'll notice that temperature begins to drop in conjunction with the fading availability of sunlight. With progressively less solar input managing to reach these depths, the water is able to hold onto less heat and gradually settles into consistently cool conditions that shift only very slowly over extended periods of time. The thermocline frequently marks the specific region where temperature decreases more sharply than in the zones above or below it, effectively creating a boundary zone between the warmer mixed layer near the surface and the substantially colder water that sits underneath. The exchange of heat becomes increasingly restricted at these depths, primarily because vertical mixing grows weaker and the sunlight that does penetrate is no longer strong enough to replace the thermal energy that gets lost. As a consequence of these factors, the seasonal temperature fluctuations that occur are considerably smaller at these depths when compared to the more dramatic swings that take place near the surface. The cooler environment found at these depths also changes the way gases dissolve in the water, which allows certain regions to maintain higher concentrations of dissolved oxygen than might otherwise be expected. This steady decline in temperature as depth increases also contributes to making the water progressively denser, a factor that plays a crucial part in shaping the large-scale circulation patterns that operate throughout the ocean. The water in the ocean becomes progressively denser as depth increases, and pressure continues to build in a steady manner. The accumulated weight of all the water sitting in the layers above creates a continuous downward force that compresses the water molecules slightly closer together than they would otherwise be. While water itself is not easily compressed under normal circumstances, over the great vertical distances found in the deep ocean, the cumulative effect of this compression becomes quite noticeable and measurable. This increased density that comes with depth affects a range of physical phenomena, including how sound propagates through the ocean, how currents are able to flow, and how suspended particles make their way downward through the water column. Other physical characteristics such as viscosity and buoyancy undergo shifts as well, which influences the behavior of both non-living materials and living organisms that inhabit these depths. The gradual increase in pressure creates what can be considered a reliable and predictable environment where conditions tend to change in a smooth manner, rather than experiencing sudden or abrupt shifts. When examined across extended depth ranges, this rising density plays an important role in helping to maintain the stable layering effect that keeps the surface-influenced waters clearly separate from the deeper ocean zones below. When you reach depths around 100 meters, the influence that surface waves exert on water movement begins to fade noticeably. The circular orbital motion that is created by waves at the surface grows progressively weaker as depth increases, which leads to the development of a calmer physical setting, where the up and down displacement of water becomes increasingly minimal. Water at this particular level tends to move in wider and slower patterns that are shaped primarily by regional scale currents, rather than by the immediate surface activity happening overhead. With reduced mechanical stirring taking place, fine particles suspended in the water are able to remain hanging in place for considerably longer periods before they finally begin to settle downward. Temperature differences between neighboring layers of water become easier to detect and measure as the level of turbulence decreases. This quieter zone represents a gradual transition from the actively mixed conditions of the upper ocean toward the more stable waters found at mid-depth levels. Across broad geographic areas, the diminishing effect of surface waves helps to create and maintain consistent environmental conditions that tend to evolve and change only slowly over extended periods of time. Wind serves as the primary driver of mixing in the upper ocean, generating patterns of gentle circulation near the surface. Persistent winds blowing across the water transfer their energy downward, which creates broad rotating systems known as gyres, along with more local currents that transport heat, nutrients, and dissolved gases from one location to another. This mixing action helps to keep both salinity and temperature fairly even and uniform within the surface layer across large geographic distances. Floating organic debris and microscopic forms of life are carried sideways and horizontally by these slow-moving circulation patterns. The exchange with the atmosphere overhead continues in an active manner, which allows oxygen to dissolve into the water, while at the same time permitting carbon dioxide to be released into the air or absorbed from it, depending on the specific regional conditions and patterns. This constant state of movement prevents water from remaining stagnant or sitting completely still for extended periods, and it keeps the biochemical cycles operating at a steady pace. These various processes working together give the upper ocean its characteristically dynamic nature before conditions transition to become more distinctly layered in the zones below. In the regions deeper beneath the surface, the layers of water grow increasingly stable and encounter far less disturbance from above. The reduced level of turbulence allows distinct layers that possess different temperatures and densities to remain firmly in place without experiencing frequent mixing with adjacent layers. The vertical movement of heat and nutrients slows down considerably, and the boundaries that exist between different layers can hold steady and persist for long stretches of time. Suspended particles present in the water drift gradually downward through what is now relatively still and calm water. Sound waves are able to travel more consistently through these depths because fewer disturbances originating from the surface manage to reach down this far. The stable physical structure that develops supports the existence of predictable physical conditions across wide geographic regions. This progressive layering represents a steady transition toward environments where change takes place at a notably slower rhythm than what occurs closer to the surface. Light continues its steady process of fading as you make your descent through the upper regions of the ocean. Water molecules and small particles suspended in the water continuously work to absorb and scatter the available light, which steadily reduces the overall brightness of the environment. At depths in the vicinity of 200 meters, the ocean makes its entry into a region that is frequently referred to as the twilight zone. Within this particular depth range, only weak and residual light from the surface, high above, manages to remain present. And what does reach this far is no longer strong enough to support the process of photosynthesis. What an observer can see at these depths depends to a large extent on the remaining blue wavelengths that manage to filter their way down from the layers above. Temperature at this level is typically cooler than what is found in the mixed layer closer to the surface, and the day-to-day changes in temperature are quite small. Water moves in a slow manner, with currents being driven by the broader patterns of ocean circulation, rather than by local winds acting at the surface. Organic material continues its steady descent, sinking down from the productive layers above and offering a continuous but rather limited source of energy for organisms at this depth. The twilight zone effectively serves as a transitional environment positioned between the well-lit surface ocean above and the considerably darker regions that lie deeper down below. Throughout the twilight zone, only faint traces of blue light manage to filter their way down from the distant surface. The light that does remain is scattered and weak in intensity, offering very little in the way of visual contrast within the surrounding water mass. Blue wavelengths possess the ability to penetrate to greater depths than other colors in the spectrum, while most of the longer wavelengths have already been completely absorbed in the shallower layers higher up. This leftover light frequently gets scattered further by suspended particles drifting in the water, which creates an even and subdued glow, rather than producing any clear directional beams of light. The dim intensity that characterizes this zone influences how organisms are able to detect movement and identify shapes in the mid-water column environment. When examined across broad geographic regions, the level of illumination present changes in a gradual manner with increasing depth, rather than experiencing any sharp or sudden drop-off. These particular conditions work together to establish a consistent low-light environment that stretches across much of the mid-depth ocean waters. In the regions deeper below the surface, there simply isn't enough light remaining to support the process of photosynthesis any longer. The energy that is available from whatever sunlight manages to penetrate this far is too weak and insufficient to drive the complex biochemical reactions that are necessary for primary production to occur. As a direct result of this limitation, new organic matter is only very rarely created at these particular depths, which means that ecosystems operating here must rely almost entirely on material that has its origins in the higher, more productive layers above. Sinking particles that include microscopic debris and various forms of waste material provide a steady but quite modest supply of nutrients to support life. The complete absence of photosynthetic activity means there is also reduced production of oxygen within this zone, which makes the levels of dissolved oxygen that are present dependent primarily on circulation patterns that bring it in from other areas of the ocean. Biological activity certainly continues at these depths, but it is sustained mainly by organic material that was formed earlier in shallower waters and has since descended. This fundamental shift marks a clear and important transition from productivity that is driven directly by available light to a state of dependence on energy and nutrients that must be transported from elsewhere. Water temperature continues along its gradual path of decline as you examine the deeper layers of the ocean. With almost no solar heating managing to reach these depths, the water settles into consistently cold conditions that remain remarkably stable throughout the entire year. Seasonal changes that occur at the surface have very little measurable impact at these depths, primarily because vertical mixing is quite limited and ineffective at transferring heat downward. The increasingly cool environment contributes to higher water density and plays a role in helping to maintain the distinctly layered structure of the water column. The transfer of heat at these depths happens very slowly and occurs mainly through large-scale circulation patterns rather than through any rapid local mixing processes. These remarkably steady temperatures work to create highly predictable physical conditions across vast oceanic areas spanning great distances. The gradual cooling that continues with depth reflects and demonstrates how the influence of energy from the surface progressively fades away as you move deeper into the ocean. By the time you reach depths around 300 meters, the pressure present is already several times greater than what you would encounter at the surface level. The accumulated weight of all the water in the layers above creates a force that presses down continuously and distributes itself evenly across all surfaces and in all directions. This substantial pressure has significant effects on how gases behave in the water, causing any unprotected airspaces to shrink considerably in volume. The fundamental physical properties of the water itself remain stable and consistent, though the density is measurably higher than what is found in the shallower layers closer to the surface. Materials and biological structures present at this depth experience constant compression forces, though these forces remain steady without experiencing sudden changes or fluctuations. The environment continues to shift in a gradual and steady manner as depth continues to increase further. These highly predictable pressure conditions play an important role in shaping how biological tissues are structured and how cellular processes are able to function effectively in these mid-water habitats. Sound possesses the ability to travel across great distances when moving through the dense water, characteristic of the mid-depth ocean environment. The uniform density found at these levels, combined with reduced disturbance effects from the surface, allows acoustic waves to move forward and propagate with relatively little loss of their energy along the way. The gradients in temperature and pressure that exist influence both how fast sound is able to travel and in what direction it tends to move as it passes across different layers of water. The characteristically low background noise present in deeper water creates conditions that can allow even faint sounds to remain detectable across impressively long ranges. This particular property holds importance both for natural marine communication between organisms and for various scientific measurement techniques employed by researchers. Acoustic signals traveling through the water may curve or bend gradually as they make their way through layers that possess different densities. The mid-depth ocean therefore provides and offers a stable physical medium that supports consistent and reliable sound transmission across considerable distances. In the regions farther below the surface, suspended particles present in the water drift slowly downward as they make their way through the water column. These particles are composed of various materials, including broken bits and fragments of organic matter, mineral grains of various sizes, and microscopic remains of organisms that descend under the steady pull of gravitational force. The significantly reduced turbulence that characterizes these depths allows the particles to settle at a gradual and steady pace, rather than being rapidly mixed upward by strong currents or eddies. Their downward movement makes an important contribution to the continuous transfer of material from the productive upper layers toward the deeper regions of the ocean. As these particles make their descent, some portion of them gets broken down and decomposed by microorganisms present in the water, a process which releases dissolved nutrients into the surrounding water mass. This slow process of downward transport forms a lasting and persistent link between the biological processes occurring at the surface and the deeper environments found below. Over long periods spanning many years, the cumulative effect of this settling material helps to distribute nutrients throughout the vast interior spaces of the ocean. The twilight zone is characterized by large open spaces that contain relatively little in the way of physical structure or solid features. Unlike coastal areas or shallow reef environments where structure is abundant, this mid-water environment is defined mainly by enormous volumes of water that contain very few solid features or obstacles. The notable lack of physical obstacles allows currents to move in broad and gentle patterns that extend over extensive geographic distances. Visibility remains limited throughout this zone due to the combination of low available light and suspended material drifting in the water. But the physical space itself is remarkably expansive and unbroken by barriers. Organisms that make their home in this zone typically occupy different vertical levels within the water column rather than depending on or relying upon fixed surfaces for attachment or shelter. The distinctly open nature of this habitat leads naturally to populations that are widely dispersed across large areas. This spatial uniformity and lack of physical structure is highly characteristic of much of the mid-depth ocean environment. By the time you reach depths around 500 meters, natural light has become very limited in its availability and intensity. The remaining illumination present is typically far too weak to provide clear visual detail, and appears instead as merely a faint and scattered glow emanating from somewhere above. Most of the wavelengths in the light spectrum have already been absorbed by the water column, leaving behind only minimal amounts of blue light that continues to weaken progressively with each additional meter of depth. The substantially reduced brightness that characterizes this environment affects the ability of organisms to rely on visual detection and encourages them to develop and use other sensory mechanisms for navigation and hunting. Temperature at this particular level is generally cool and undergoes very little change over extended periods of time. Water movement remains slow and is shaped primarily by large-scale circulation patterns, rather than being influenced by surface weather conditions. These notably stable conditions work together to define a consistent low-light environment that extends across wide oceanic regions. A significant number of organisms that make their living at this level possess eyes that have become specially adapted to detect the faint light that is available. Their visual systems frequently include adaptations that provide increased sensitivity to low-intensity illumination, which allows them to pick up and register subtle contrasts that would otherwise go unnoticed. Larger pupils or specialized structures present in the retina can substantially improve their ability to register and respond to the limited number of photons that are available. Such adaptations provide valuable assistance with orientation in the water column and with recognizing movement in these dim conditions. The energy that organisms invest in maintaining their vision capabilities must be carefully balanced against the ongoing need to conserve their metabolic resources for other essential functions. These visual features reflect a gradual process of adjustment to environments where light is certainly present, but remains quite scarce. The adaptations that have evolved are typically functional and practical in nature, rather than being designed to provide the kind of bright and detailed visual information that would be available in shallower waters. In the regions deeper beneath the surface, water tends to move in a generally slow and steady manner that varies little over time. The currents operating at these depths are driven mainly by differences in temperature and salinity, that exist across large geographic regions, rather than by local forces. The absence of strong wave action and surface turbulence significantly reduces the short-term changes and variations in flow patterns that might otherwise occur. Suspended material and dissolved substances present in the water get transported gradually over long distances as the slow currents carry them along. This steady and reliable circulation plays an important role in helping to distribute oxygen and nutrients throughout the deeper layers of the ocean. Physical conditions at these depths stay remarkably consistent for extended periods, experiencing only minor fluctuations rather than dramatic swings. The overall effect that emerges is that of a calm and stable water column that changes and evolves at a notably measured and predictable pace. The energy that sustains life in deeper waters frequently comes from organic material that sinks down from the productive zones above. This descending material is composed of various components, including microscopic remains of plants, waste particles produced by organisms, and fragmented biological debris that makes its way down through the water column at a gradual pace. As this material moves steadily downward through the depths, certain portions of it get consumed by organisms or undergo decomposition, processes which release dissolved nutrients into the surrounding layers of water. The remaining fraction that escapes consumption or decomposition continues its journey toward even greater depth, where it provides a steady but decidedly limited supply of energy to support life. This downward transfer of material and energy supports the existence of food webs that are unable to rely on sunlight as their primary energy source. The overall process creates and maintains important links between the productive surface regions where photosynthesis occurs and the deeper environments below, through this continuous exchange of material. At depths in the vicinity of 700 meters, temperatures are typically cold and remain notably stable over time. Seasonal variations that occur at the surface very rarely manage to reach down to this level, due to the limited amount of vertical mixing that takes place. The water at this depth stays confined within a narrow temperature range that shifts only very slowly over extended periods. Such remarkable stability in temperature supports the existence of highly predictable physical conditions across broad geographic areas of the ocean. Differences in density between the various layers of water help to maintain and preserve the separation from the warmer water that exists above. The transfer of heat at these depths happens mainly through the slow operation of large-scale circulation patterns, rather than through local turbulence or rapid mixing processes. These various factors working together contribute to the creation of a consistent thermal environment throughout the mid-depth waters of the ocean. Pressure continues along its path of steady increase in a predictable manner as depth continues to grow. Each additional layer of water positioned above adds its incremental force to the total, and this force spreads itself evenly in all directions throughout the surrounding water. Although the change in pressure per individual meter of depth is relatively small, the cumulative effect that builds up becomes quite significant when measured across hundreds of meters of vertical distance. The physical properties of fluids and dissolved gases present undergo gradual adjustments under the influence of this ongoing compression. Structures that lack internal air spaces tend to remain largely unaffected by sudden variation and continue to function normally. The progression of increasing pressure is remarkably smooth and continuous, with no sharp or abrupt shifts occurring between neighboring layers of water. This predictable and steady increase in pressure plays a fundamental role in shaping the long-term environmental conditions found throughout the deep ocean. In the regions deeper beneath the surface, the ocean undergoes a transition into what is known as the dark zone, a realm where sunlight is no longer able to reach. Throughout this particular region, natural illumination coming from above is effectively and completely absent. Visual conditions in this zone depend mainly on non-solar sources of light, such as bioluminescence, or they simply remain uniformly dark throughout. Temperature throughout the dark zone is generally quite low and varies very little across the changing seasons. Water movement remains slow and is guided primarily by broad circulation patterns that operate on large scales rather than being influenced by local disturbances or surface conditions. The environment becomes increasingly more uniform in its characteristics as depth continues to increase. This fundamental transition marks the boundary zone between the faintly lit waters that exist above and the fully dark ocean layers that extend below. Within the dark zone itself, visual conditions approach a state of near total darkness. Without any incoming sunlight to provide illumination, the ambient brightness remains extremely low throughout most of the water column. objects and organisms are exceedingly difficult to make out or distinguish without the aid of specialized sensory adaptations that have evolved for this purpose. The complete absence of light also removes the possibility of photosynthetic activity entirely from this environment. Biological processes that continue to operate at these depths must depend entirely on previously formed organic material that has descended from above, or on chemical energy pathways that do not require light. Sound and the detection of subtle movements in the water become far more reliable environmental cues for organisms than any visual signals could possibly be. The overall setting that characterizes this zone remains stable, quiet, and consistently dark over very long periods of time. By the time you reach depths around 1,000 meters, water temperature is usually just barely above the freezing point. The complete absence of solar heating allows the water to maintain itself within a narrow and consistently cold temperature range that persists throughout the entire year. Heat exchange with the upper layers of the ocean is quite limited at this depth, primarily because vertical mixing is very weak and ineffective at this level. The persistently cold conditions contribute to increased water density and play a role in helping to maintain the stable stratification of the water column. Dissolved gases remain present in the water, with their concentrations being influenced primarily by slow circulation patterns rather than by local changes in temperature. Seasonal variations that occur at the distant surface have virtually no measurable effect at these great depths. This steady and unchanging thermal environment is typical and characteristic across many deep ocean regions around the world. A large proportion of deep-sea organisms have evolved strategies to conserve energy through slow and deliberate movement patterns. The limited availability of food in these environments strongly favors behaviors and adaptations that work to reduce metabolic demand over long periods of time. Muscular activity among these organisms is often measured and highly efficient in nature, rather than being continuous or energy intensive. Energy budgets must be carefully balanced to support basic survival in conditions where new resources arrive only irregularly and unpredictably. The physiological processes operating within these organisms tend to function at considerably slower rates when compared to similar processes in organisms living in warmer and brighter waters, closer to the surface. Such adjustments and adaptations allow for sustained function and survival, despite the significantly restricted energy input available in these depths. These patterns of behaviour and physiology reflect long-term adaptation to an environment that is stable and predictable, but decidedly limited in terms of available resources. In the regions farther below the surface, the availability of food becomes increasingly limited and irregular in its distribution. Organic material that arrives from the productive upper layers is substantially reduced in quantity, because much of it has already been consumed or decomposed during its descent before managing to reach these greater depths. The remaining supply that does make it this far becomes spread out and dispersed over large volumes of water, which creates an overall concentration that is quite low. Periodic inputs of energy may still occur when larger particles or aggregations of material descend from above, but these events are far from frequent or regular. Organisms inhabiting these depths often must rely on highly efficient detection mechanisms and careful utilization of any available nutrients they manage to encounter. The pronounced scarcity of resources plays a major role in shaping both population density and the general activity levels of organisms living here. This gradual decline in available energy supply is highly characteristic of the deeper layers of the ocean. The substantial water pressure present at these depths exerts significant effects on the structure and function of biological tissues. Cells and membranes must function while under constant compression, which influences the nature of molecular interactions taking place within them. Proteins and enzymes present in these organisms are specifically adapted to remain stable and maintain their activity despite the surrounding force being applied. Gas-filled spaces are generally either completely absent or greatly reduced in size to prevent deformation or collapse under pressure. The balance of fluids within tissues is carefully maintained through the operation of specialized biochemical regulation systems that have evolved for this purpose. These various adjustments and adaptations support the continuation of normal physiological processes, even under the sustained pressure present at great depth. The influence of this pressure is continuous and constant, rather than variable, which reflects the notably steady environmental conditions that characterize the deep ocean environment. By the time you reach depths around 1,500 meters, the water column has become largely uniform in its temperature characteristics. the vertical gradients in temperature have grown quite weak, and the differences that exist between neighboring layers are minimal and barely detectable. The absence of any solar influence, combined with very limited mixing between layers, contributes significantly to this remarkable consistency. Large masses of water can persist while maintaining similar thermal properties across wide geographic regions spanning great distances. The transfer of heat at these depths happens mainly through the slow operation of global-scale circulation patterns, rather than through any local processes. The stable temperature profile that results supports the existence of highly predictable physical and chemical conditions throughout these zones. Such uniformity in thermal characteristics is a defining and characteristic feature of many deep mid-ocean zones around the world. Certain species, such as lanternfish, engage in vertical migration patterns to feed in the higher, more productive layers of the ocean. This movement typically follows the daily cycles of light availability, with individual fish rising toward shallower waters during certain periods and then returning to deeper levels afterward to rest or avoid predation. This behavior provides them with valuable access to food resources in areas where organic material is considerably more plentiful and abundant, while simultaneously allowing them to maintain their primary residence in the darker and cooler depths, where competition may be less intense. Energy use and expenditure during these substantial vertical movements is moderated and kept reasonable through steady swimming patterns and the efficient function of their muscle systems. The migration pattern itself contributes to the transfer and redistribution of nutrients between different depth layers over the course of time. Such patterns of vertical migration are observed across broad ocean regions throughout the world, rather than being limited to isolated spots or specific locations. The activity reflects an organized and adaptive response to the changing patterns of light availability and resource distribution that characterize different depths. In the regions deeper beneath the surface, many animals have come to rely heavily on sensitive lateral line systems to detect motion and movement in their surroundings. These specialized sensory structures are capable of picking up small vibrations and detecting subtle pressure changes within the surrounding water mass. The detection of nearby movement becomes entirely possible even in situations where visibility is extremely limited or completely absent. The lateral line system operates and functions continuously without any dependence on external light sources. Subtle shifts in water current or the presence of other organisms moving nearby can be readily recognized and identified through the operation of this remarkable sensory mechanism. The energy expenditure required for this type of sensing remains quite low when compared to the energy that would be needed for constant active searching, using vision or other senses. This evolutionary adjustment provides important support for orientation and interaction with the environment and with other organisms within this dim and stable deep water environment. The dark zone contains vast expanses and areas characterized by very low population density throughout. Large volumes of water serve to separate individual organisms across considerable distances from one another. The limited food supply, combined with slow energy input, severely restricts the total number of inhabitants that can be successfully supported in any given area. Encounters between individual organisms may be quite infrequent due to the expansive nature of the space and the low density of life present. Biological activity certainly continues to take place throughout the zone, but it remains spread thinly across the enormous water column. The environment remains physically uniform throughout, with very few structural features or landmarks to provide reference points. This characteristically sparse distribution of life is typical of many deep ocean regions across the world. By the time you reach depths around 2,000 meters, the pressure present has become sufficient to compress any unprotected airspaces quite significantly. Gas-filled cavities, if they were present in an organism or structure, would experience a substantial decrease in volume under the surrounding force being applied. Most deep-sea organisms have therefore evolved to lack any structures that would rely on internal air for buoyancy or other functions. Fluids and solid tissues remain functional and relatively unaffected because they are largely incompressible by their nature. Equipment and materials that are used in deep exploration activities must also take careful account of this constant compression force in their design. The pressure continues to increase in a gradual manner with each additional interval of depth reached. Environmental conditions remain steady and consistent, rather than fluctuating over short periods of time. The massive deep water masses present in the ocean often move quite slowly as integral parts of what is known as global thermohaline circulation. Differences in temperature and salinity between different water masses drive large-scale flows that work to connect distant ocean basins located on opposite sides of the planet. These currents operate over very long timescales measured in years or decades, and serve to transport heat, dissolved gases, and nutrients across vast distances. Movement patterns are generally measured and described in terms of slow and persistent pathways, rather than rapid streams or jets. This global circulation system makes crucial contributions to the long-term balance of ocean chemistry throughout the world. Water located at great depth may remain within the same general circulation pathway for extended durations lasting many years. This steady and persistent motion forms an essential and fundamental component of the planet's overall climate system. In the regions deeper beneath the surface, organic debris continues its ongoing process of settling down from the productive upper layers far above. This descending material includes fragmented remains of plankton organisms, fine waste particles of various types, and microscopic mineral grains that move steadily downward under the constant influence of gravitational force. The rate at which this descent occurs is generally quite slow, because the resistance provided by the water and the presence of weak currents work together to limit any rapid downward movement. During the long journey downward through the water column, some portion of the material inevitably gets consumed by organisms or undergoes decomposition through bacterial action, processes which release dissolved nutrients into the surrounding water mass. The remaining fraction that survives this consumption and decomposition continues deeper still, making an important contribution to the long-term transfer of carbon and other essential elements toward the ocean floor. This steady input of material from above provides a modest but continuous source of energy that helps to support the deeper ecosystems present. Over extended periods spanning many decades or centuries, the gradual accumulation of such particles exerts significant influence on the chemical conditions found throughout the lower regions of the water column. A substantial number of deep-sea fish species have evolved to possess reduced muscle mass as an energy conservation strategy. Lower overall muscle volume works to decrease the metabolic demand placed on the organism and allows for sustained function in environments where food remains persistently scarce. Movement patterns among these fish tend to be measured, economical, and highly efficient in nature, rather than being frequent, rapid, or energy intensive. Energy that is saved through this reduced activity level can then be allocated and directed toward other essential physiological processes, such as tissue maintenance and reproduction. The body structures of these fish often place emphasis on buoyancy control mechanisms instead of developing strong propulsion systems for rapid swimming. These various physiological adjustments and adaptations support long-term survival under conditions that are stable and predictable, but decidedly limited in terms of available resources. This pattern of reduced muscle mass and economical movement is common and widespread among species that inhabit the consistently dark mid-depth waters of the ocean. By the time you reach depths around 2,500 meters, temperatures remain consistently cold throughout the entire year without significant variation. The complete absence of solar influence, combined with minimal vertical mixing between layers, works to maintain a narrow thermal range that varies little over time. Seasonal changes that occur at the distant surface rarely, if ever, affect these great depths in any noticeable or measurable way. The persistently cold environment makes an important contribution to higher water density and helps maintain the stable layering characteristic of these depths. Heat transfer at this level occurs mainly through the slow movement of large water masses as part of broader circulation patterns. Chemical processes taking place in the water proceed at steady and predictable rates under these constant environmental conditions. Such remarkable thermal stability is highly characteristic of much of the deep ocean interior throughout the world. Bristlemouth fish have gained recognition for their highly efficient feeding strategies that allow them to thrive in low-energy environments. Their feeding behavior focuses primarily on the capture of small drifting prey organisms with minimal expenditure of effort or energy. Energy intake must be balanced with great care against their metabolic needs due to the limited and unpredictable food supply available in their habitat. A range of physiological adaptations supports their sustained function in the cold and high-pressure water environment they inhabit. Population numbers of bristlemouth fish can actually be quite substantial when measured relative to the available resources in their environment, which demonstrates the effectiveness of their efficiency. Their widespread presence throughout the deep ocean illustrates clearly how energy conservation strategies can support persistence and success in deep ocean habitats. This example reflects and demonstrates a broader pattern of economical resource use that is common among many mid-depth organisms. At depths of approximately 50 meters beneath the surface, light begins to soften noticeably and colors start to fade from view. As sunlight travels downward through seawater, the longer wavelengths such as red and orange are absorbed first by the water molecules. This selective absorption leaves predominantly blue tones. To continue their journey deeper into the ocean, the gradual filtering effect reduces visual contrast significantly and alters the appearance of suspended particles and drifting organisms that move through the water column. The remaining light becomes increasingly diffuse as scattering intensifies with depth. This creates evenly distributed illumination throughout the water rather than the direct beams seen closer to the surface. Physical conditions remain relatively calm when compared with the turbulent surface environment, though slow-moving currents continue to transport nutrients and microscopic life between neighboring water masses. Visibility can vary considerably depending on the density of plankton and the concentration of dissolved substances in the water, yet the overall trend remains consistent. A steady reduction in brightness as depth increases. This transition marks the early stage of the descent toward lower light environments where visual cues become progressively less dominant for many marine species that inhabit these depths. Surface waters are generally warmer due to their direct contact with solar radiation throughout the daylight hours. Continuous exposure to sunlight allows the upper ocean to absorb and retain heat energy, producing temperatures that fluctuate according to latitude, season, and prevailing weather patterns. Wind-driven mixing distributes this accumulated warmth through what is known as the mixed layer, preventing the formation of sharp temperature differences within the upper tens of meters. Exchanges with the atmosphere also influence temperature through processes such as evaporation, precipitation, and heat transfer that occurs during changing air conditions. In many regions across the world's oceans, this warmer surface layer forms a distinct boundary above the cooler water that lies below it. It creates a gradual thermal gradient known to oceanographers as the thermocline. The presence and depth of this gradient vary considerably across different ocean basins, but consistently reflect the diminishing influence of solar heating as depth increases. These temperature patterns affect fundamental properties such as water density, circulation patterns, and the distribution of dissolved gases throughout the water column. they contribute significantly to stable stratification between the upper layers and the deeper waters below. Further below the surface, temperature decreases steadily as sunlight weakens and eventually disappears. With reduced solar input reaching these depths, deeper water retains far less heat and approaches consistently. Cool conditions that change only slowly over extended periods of time. The thermocline often marks the zone where temperature drops more noticeably than in adjacent layers, effectively separating the warmer, mixed layer above from the colder water beneath. Heat exchange becomes increasingly limited at these depths because vertical mixing is considerably weaker and sunlight is insufficient to replenish any thermal energy that is lost. As a result, temperature variations across different seasons are minimal when compared with the dramatic shifts observed near the surface. The cooler environment influences the solubility of gases in the water, allowing higher concentrations of dissolved oxygen to persist in certain regions where circulation patterns bring it from above. This gradual decline in temperature also contributes to increasing water density with depth, which plays a central role in driving large-scale ocean circulation patterns that connect different parts of the global ocean. Ocean water becomes progressively denser with depth as pressure steadily increases beneath the weight of water above. The accumulated weight of the overlying water column exerts a continuous force that compresses water molecules slightly closer together. Although water is only minimally compressible as a substance, the cumulative effect across great depths leads to measurable increases in overall density. Higher density influences multiple physical processes, including how sound travels through the water, how currents move and interact, and how suspended particles settle gradually through the water column. Physical properties such as viscosity and buoyancy are also affected by these changes, shaping the behavior of both inorganic material and living organisms that inhabit these environments. The steady rise in pressure creates a highly predictable environment in which conditions change gradually and smoothly rather than abruptly. Over extended depth ranges spanning hundreds or thousands of meters, this increasing density contributes to stable layering that effectively separates surface-influenced waters from the deeper ocean below. At depths of around 100 meters, waves generated at the surface have far less influence on water movement than they do higher up. The orbital motion generated by surface waves diminishes steadily with depth, resulting in a considerably calmer physical environment where vertical displacement becomes quite limited. Water in this depth range tends to move in broader and slower patterns than at the surface. These patterns are driven more by regional currents and large-scale circulation than by immediate surface conditions or local weather events. The reduced mechanical mixing allows fine particles to remain suspended in the water column for longer periods, before eventually settling downward under gravity. Temperature differences between neighboring layers become more noticeable and stable as turbulence decreases. This quieter setting supports a gradual transition from the actively mixed upper ocean to the more stable mid-depth waters below. Over wide areas of the ocean, the diminished effect of surface waves contributes to consistent conditions that change only slowly over time, creating an environment quite different from the dynamic surface zone. The upper ocean is mixed continuously by wind, creating gentle circulation patterns near the surface. Persistent winds transfer momentum to the water below, generating broad gyres and local currents that redistribute heat, nutrients, and dissolved gases across vast distances. This mixing action helps maintain relatively even salinity and temperature within the surface layer across large horizontal distances. Floating organic material and microscopic life are carried horizontally by these slow circulations, distributing them across wide areas. Exchange with the atmosphere remains active at the surface, allowing oxygen to dissolve into the water while carbon dioxide can be released or absorbed, depending on regional conditions and biological activity. The continual movement prevents long-term stagnation of the water and supports steady biochemical cycles that are essential for marine life. These processes establish the fundamentally dynamic character of the upper ocean before conditions become more stratified and stable in the layers below. Further below the surface, water layers become increasingly more stable and less disturbed by external forces. Reduced turbulence allows distinct layers with different temperatures and densities to persist without frequent mixing events. Vertical exchange of heat and nutrients slows considerably, and the boundaries between different layers can remain in place for extended periods without disruption. Suspended particles drift gradually downward through relatively calm water rather than being mixed vigorously in multiple directions. Sound transmission becomes more consistent because fewer surface disturbances penetrate down to these depths. The stable structure that develops supports predictable physical conditions across broad regions of the ocean. This stratification marks a steady progression toward environments where change occurs at a much slower pace than near the surface. Light continues to diminish steadily as depth increases through the upper ocean and into the mid-water zone. Absorption by water molecules and scattering by small suspended particles steadily reduce the overall brightness available for vision. Colors become limited mainly to shorter blue wavelengths, while longer wavelengths have already been absorbed higher up, and contrast decreases noticeably across the visual field. The reduced illumination affects how organisms detect shapes and movement within the surrounding water column. Photosynthetic activity declines progressively as usable light becomes less and less available to support primary production. The gradient in light intensity forms a clear vertical pattern that is repeated across most open ocean regions, regardless of location. This ongoing reduction in available light signals the approach to deeper layers, where natural illumination becomes minimal or entirely absent. At depths of around 200 meters, the ocean enters the region often referred to as the twilight zone or mesopelagic zone. In this depth range, only faint residual light from the surface remains present in the water. It is insufficient to support photosynthesis by any known organisms. Visual conditions depend largely on the remaining blue wavelengths that manage to penetrate from above, though even these are significantly weakened. Temperature is typically cooler than in the mixed layer above, and daily fluctuations are small compared to surface variations. Water movement remains slow and steady, with currents driven primarily by broader ocean circulation patterns. Rather than local wind forcing, organic material continues to sink gradually from the upper productive layers, providing a steady but quite limited energy source for organisms at this depth. The twilight zone represents an important transitional environment between the illuminated surface ocean and the completely dark regions that lie below. In the twilight zone, only faint blue light remains from the distant surface above. The remaining illumination is diffuse and weak, providing very limited visual contrast within the surrounding water. Shorter blue wavelengths manage to penetrate deeper than other colors in the spectrum, while most longer wavelengths have already been absorbed in the waters above. This residual light is often scattered by suspended particles drifting through the water, creating an even and subdued brightness. rather than directional beams that would allow clear vision. The reduced intensity influences significantly how organisms detect movement and distinguish shapes in the mid-water column. Over broad regions of the ocean, the level of illumination changes slowly and gradually with depth, rather than dropping off abruptly. These conditions establish a consistent low-light environment that persists across much of the mid-depth ocean, regardless of surface conditions above. Further below the surface, photosynthesis is no longer possible due to the severely limited light available. The available energy from sunlight is insufficient to support the complex biochemical reactions required for primary production by phytoplankton. As a result, new organic matter is rarely created at these depths through photosynthetic processes. Ecosystems operating here depend entirely on material originating from the higher layers above. Sinking particles, including microscopic debris and waste products from organisms living in shallower water, provide a steady but quite modest source of nutrients and energy. The absence of photosynthesis leads to significantly reduced oxygen production within this zone, making dissolved oxygen levels dependent primarily on circulation patterns from other regions rather than local generation. Biological activity continues at these depths, but it is supported mainly by previously formed organic material that descends from above. This shift marks a clear and important transition from light-driven productivity to complete reliance on transported energy sources. Water temperature continues to decline gradually in these deeper layers. With minimal solar heating reaching down from above, the water approaches consistently cold conditions that remain remarkably stable throughout the year. Seasonal changes that occur at the surface have very little influence at these depths, because vertical mixing is quite limited and slow. The cooler environment increases water density and supports the persistence of distinct layered structure in the water column. Heat transfer occurs slowly through large-scale circulation patterns, rather than through rapid local mixing events. These steady temperatures contribute to highly predictable physical conditions across wide oceanic areas. The gradual cooling with depth reflects clearly the decreasing influence of surface energy input, as distance from the sun-warmed surface increases. At depths of around 300 meters, pressure is already several times greater than the pressure experienced at the surface. The cumulative weight of the overlying water column exerts a continuous and evenly distributed force on all surfaces within the water. This pressure affects the behaviour of gases dissolved in the water, reducing the size of any unprotected airspaces that might exist. Physical properties of the water itself remain stable, though density is slightly higher than in the shallower layers above. Materials and structures present at this depth experience constant compression without sudden variation or change. The environment changes in a steady and predictable manner as depth increases further downward. Such predictable pressure conditions shape fundamentally how biological tissues and cellular processes must function in mid-water habitats. Sound can travel remarkably long distances through the dense water of the mid-depth ocean. The uniform density and reduced surface disturbance allow acoustic waves to propagate with relatively little loss of energy over great distances. Temperature and pressure gradients influence both the speed and direction of sound transmission as it passes across different layers. Low background noise in deeper water can permit even faint sounds to remain detectable over extended ranges spanning many kilometers. This property is important not only for natural marine communication between animals, but also for scientific measurement techniques used to study the ocean. Acoustic signals may bend gradually as they pass through layers with different physical properties and densities. The mid-depth ocean, therefore, provides a stable and consistent medium for sound propagation. Further below the surface, suspended particles drift slowly through the water column under the influence of gravity. These particles include fragments of organic matter, mineral grains, and microscopic remains that descend steadily under the influence of gravity. The reduced turbulence at these depths allows them to settle at a gradual and steady pace, rather than being rapidly mixed upward by turbulent currents. Their downward movement contributes to the continuous transfer of material from the upper productive layers toward the deeper regions of the ocean. As they descend through the water column, some particles are broken down by microorganisms, releasing dissolved nutrients back into the surrounding water. This slow downward transport forms a persistent link between surface processes and the deeper environments far below. Over long periods spanning years and decades, the cumulative effect of this particle rain supports nutrient distribution throughout the ocean interior. The twilight zone contains large open spaces with relatively little physical structure to orient by. Unlike coastal regions or shallow coral reefs where solid structures are abundant, this mid-water environment is defined mainly by vast volumes of water with very few solid features or landmarks. The absence of physical obstacles allows currents to move in broad and gentle patterns across extensive distances. Visibility remains quite limited due to low light levels and suspended material in the water. But the physical space itself is expansive and continuous in all directions. Organisms within this zone often occupy different vertical levels, rather than relying on fixed surfaces for shelter or attachment. The open nature of the habitat contributes to widely dispersed populations spread across enormous volumes. This spatial uniformity is characteristic of much of the mid-depth ocean environment. At depths of around 500 meters, natural light is very limited and approaching complete absence. The remaining illumination is typically insufficient for clear visual detail and appears as a faint and diffuse glow from above, if it can be detected at all. Most wavelengths in the visible spectrum have been absorbed by this point, leaving only minimal blue light that continues to weaken steadily with each additional meter of depth. The reduced brightness affects visual detection capabilities significantly and encourages reliance on other sensory mechanisms for orientation and hunting. Temperature at this level is generally cool and changes very little over time or across seasons. Water movement remains slow and steady, shaped primarily by large-scale circulation patterns rather than surface weather events. These stable conditions define a consistent low-light environment across wide oceanic regions. Many organisms living in this layer have eyes specifically adapted to detect extremely faint light. Their visual systems often include increased sensitivity to low-intensity illumination, allowing detection of subtle contrasts that would be invisible to surface-adapted eyes. Larger pupils or specialized retinal structures can improve significantly the ability to register the limited photons available at these depths. Such adaptations support basic orientation and the recognition of movement in dim conditions where even faint light provides useful information. Energy investment in maintaining vision is carefully balanced with the need to conserve metabolic resources in a food-limited environment. These features reflect gradual evolutionary adjustment to environments where light is present but extremely scarce. The adaptations are typically functional rather than specialized, for the bright visual detail possible near the surface. Further below the surface, movement of water is generally slow and steady rather than turbulent. Currents in these depths are driven mainly by differences in temperature and salinity across large regions, rather than by wind or waves. The absence of strong wave action reduces short-term variability in flow patterns considerably. Suspended material and dissolved substances are transported gradually over long distances by these persistent currents. This steady circulation contributes importantly to the distribution of oxygen and nutrients throughout the deeper layers of the ocean. Physical conditions remain consistent for extended periods, with only minor fluctuations occurring. The overall effect is a calm and stable water column that changes at a measured pace over long timescales. Energy available in deeper waters often comes primarily from organic material sinking from the productive zones above. This material includes microscopic plant remains, waste particles, and fragmented biological debris that descend through the water column at a gradual pace under the pull of gravity. As it moves downward through successive depth layers, significant portions are consumed or decomposed by bacteria and other organisms, releasing dissolved nutrients into the surrounding layers. The remaining fraction continues its journey toward even greater depth, providing a steady but quite limited energy supply to organisms below. This downward transfer of organic matter supports food webs that do not rely directly on sunlight for their primary energy source. The overall process links the productive surface regions with the deeper environments through continuous material exchange that operates over long time scales. At depths of around 700 meters, temperatures are typically cold and remarkably stable. Seasonal variations from the surface rarely penetrate to this level due to the limited vertical mixing that occurs. The water remains within a narrow temperature range that changes only slowly over extended periods of time. Such thermal stability supports highly predictable physical conditions across broad areas of the ocean. Density differences between layers at different depths help maintain separation from the warmer water layers above. Heat transfer occurs mainly through slow, large-scale circulation patterns, rather than through local turbulence or mixing events. These factors together contribute to a consistent thermal environment in the mid-depth waters. Pressure continues to increase in a steady and highly predictable manner with each additional meter of depth. Each additional layer of overlying water adds incremental force that is evenly distributed in all directions throughout the water. Although the change per individual meter is quite small, the cumulative effect becomes significant across hundreds of meters of descent. Physical properties of fluids and dissolved gases adjust gradually under this increasing compression. Structures without internal air spaces remain largely unaffected by sudden variation because the pressure changes smoothly. The progression is smooth and continuous, with no abrupt shifts occurring between neighboring layers. This predictable increase in pressure shapes the long-term conditions experienced throughout the deep ocean environment. Further below the surface, the ocean transitions into what is called the dark zone or bathypelagic zone, where sunlight does not reach at all. In this region, natural illumination from above is effectively absent under normal conditions. Visual conditions depend mainly on bioluminescent sources produced by organisms themselves or remain uniformly dark. Temperature is generally low and varies very little across seasons or over time. Water movement is slow and steady, guided by broad circulation patterns, rather than local disturbances or weather events. The environment becomes increasingly more uniform as depth continues to increase. This transition marks the clear boundary between the faintly lit waters above and the fully unlit ocean layers below. In the dark zone, visual conditions approach near total darkness in the absence of biological light sources. Without any incoming sunlight penetrating from above, ambient brightness is extremely low across most of the water column. Objects are difficult or impossible to distinguish without specialized sensory adaptations beyond normal vision. The complete absence of light removes photosynthetic activity entirely from this depth range. Biological processes depend exclusively on previously formed organic material sinking from above or on chemical energy pathways that do not require light. Sound and subtle water movement become far more reliable environmental cues than visual signals for organisms living here. The overall setting remains stable, quiet, and consistently unlit over long periods. At depths of around 1,000 meters, water temperature is usually just above the freezing point of seawater. The complete absence of solar heating allows the water to maintain a narrow and consistently cold temperature range throughout the entire year. Heat exchange with the upper layers is severely limited because vertical mixing is quite weak at this level. The cold conditions increase water density further and contribute to the persistence of stable stratification throughout the water column. Dissolved gases remain present in the water, influenced primarily by slow circulation patterns rather than by local temperature change. Seasonal variations that occur at the surface have little or no measurable effect at these depths. This steady thermal environment is typical across many deep ocean regions around the world. Many deep-sea organisms have evolved to conserve energy through slow and deliberate movement. Limited food availability in these depths strongly favors behaviors that reduce metabolic demand over long periods. Muscular activity is often measured and highly efficient, rather than continuous or energetic. Energy budgets are carefully balanced to support basic survival in conditions where new resources arrive irregularly and unpredictably. Physiological processes tend to operate at slower rates compared with those in the warmer and brighter waters near the surface. Such adjustments allow sustained function despite severely restricted energy input from external sources. These patterns reflect long-term adaptation to a stable but resource-limited environment. Further below the surface, food availability becomes increasingly limited and irregular. Organic material arriving from the upper layers is significantly reduced because much of it has been consumed or decomposed before reaching these greater depths. The remaining supply is dispersed over enormous volumes of water, creating very low overall concentration. Periodic inputs may occur when larger particles or aggregates descend, but these events are not frequent or predictable. Organisms living here often rely on highly efficient detection and utilization of any available nutrients or food sources. The scarcity of resources shapes population density and activity levels throughout these depths. This gradual decline in available energy supply is characteristic of the deeper ocean layers. Water pressure at these depths affects significantly the structure and function of biological tissues. Cells and membranes must function under constant compression that influences molecular interactions at the most basic level. Proteins and enzymes are specifically adapted to remain stable and active, despite the surrounding pressure force. Gas-filled spaces are generally absent or greatly reduced in size to prevent dangerous deformation. Fluid balance within tissues is maintained through specialized biochemical regulation mechanisms. These adjustments support normal physiological processes under sustained high pressure. The influence is continuous rather than variable, reflecting the steady conditions of the deep environment. At depths of around 1,500 meters, the water column is largely uniform in temperature across wide areas. Vertical temperature gradients become quite weak, and differences between neighboring layers are minimal. The absence of solar influence and the limited mixing that occurs contribute to this remarkable consistency. Large water masses can persist with very similar thermal properties across wide regions spanning hundreds of kilometers. Heat transfer occurs mainly through slow global circulation patterns that operate over years and decades. The stable temperature profile supports highly predictable physical and chemical conditions. Such uniformity is a defining feature of many deep mid-ocean zones. Some species, such as lanternfish, undertake vertical migrations to feed in the higher, more productive layers. This movement typically follows daily light cycles, with individuals rising toward shallower waters during certain hours and returning to deeper levels afterward. The behavior allows access to food resources where organic material is considerably more available, while maintaining residence in the darker and cooler depths during other periods. Energy use during these vertical movements is moderated by steady swimming patterns and efficient muscle function. The migration contributes significantly to the transfer of nutrients between different depth layers over time. Such patterns are observed across broad ocean regions rather than in isolated locations. The activity reflects an organized behavioral response to changing light conditions and resource distribution. Further below the surface, many animals rely on highly sensitive lateral line systems to detect motion in the water around them. These sensory structures register small vibrations and pressure changes within the surrounding water with great precision. Detection of nearby movement becomes possible even when visibility is extremely limited or completely absent. The system functions continuously and does not depend on any external light source. Subtle shifts in current or the presence of other organisms can be recognized through this sensory mechanism. Energy expenditure required for this type of sensing remains low compared with constant active searching behavior. This adjustment supports orientation and interaction within a dim and stable environment where other senses would be less effective. The dark zone contains vast areas with very low population density compared to surface waters. Large volumes of water separate individual organisms across considerable distances. Limited food supply and slow energy input restrict significantly the number of inhabitants that can be supported in any given volume. Encounters between organisms may be quite infrequent due to the expansive space available. Biological activity continues throughout these depths, but is spread thinly across the water column. The environment remains physically uniform with very few structural features or landmarks. This sparse distribution pattern is typical of many deep ocean regions. At depths of around 2,000 meters, pressure is sufficient to compress significantly any unprotected air spaces. Gas-filled cavities, if present in organisms or equipment, would decrease substantially in volume under the surrounding force. Most deep-sea organisms therefore lack structures that rely on internal air for buoyancy or other functions. Fluids and tissues remain functional because they are largely incompressible under these conditions. Equipment and materials used in deep exploration must also account carefully for this constant compression. The pressure increases gradually and predictably with each additional depth interval. Conditions remain steady rather than fluctuating over short periods of time. Deep water masses often move slowly as part of the global thermohaline circulation system. Differences in temperature and salinity drive large-scale flows that connect distant ocean basins across the planet. These currents operate over very long timescales and transport heat, dissolved gases, and nutrients across enormous distances. Movement is generally measured in slow and persistent pathways, rather than rapid streams or jets. The circulation contributes fundamentally to the long-term balance of ocean chemistry. Water at great depth may remain within the same general circulation pathway for extended durations spanning decades or even centuries. This steady motion forms an essential component of the planet's overall climate system. Further below the surface, organic debris continues to settle gradually from the upper layers above. This descending material includes fragmented remains of plankton, fine waste particles, and microscopic mineral grains that move downward under the constant pull of gravity. The rate of descent is generally quite slow because water resistance and weak opposing currents limit rapid downward movement. During the long journey through the water column, some of the material is consumed by organisms or decomposed by bacteria, releasing dissolved nutrients into the surrounding water. The remaining fraction continues deeper still, contributing to the long-term transfer of carbon and other essential elements. This steady input provides a modest but continuous source of energy to the deeper ecosystems. Over extended periods spanning many years, the accumulation of such particles influences chemical conditions throughout the lower water column. Many deep-sea fish have evolved reduced muscle mass as a strategy to conserve energy. Lower muscle volume decreases significantly the metabolic demand of the organism and allows sustained function where food resources are scarce and unpredictable. Movement tends to be measured and highly efficient, rather than frequent or rapid. Energy saved through reduced activity levels can be allocated to other essential processes such as cellular maintenance and reproduction. Body structures often emphasize buoyancy control mechanisms instead of strong swimming propulsion. These physiological adjustments support long-term survival under stable but severely resource-limited conditions. The pattern is common among many species that inhabit the consistently dark mid-depth waters. At depths of around 2,500 meters, temperatures remain consistently cold throughout the entire year. The complete absence of solar influence and minimal vertical mixing maintain a narrow thermal range. Seasonal changes that occur at the surface rarely affect these depths in any noticeable way. The cold environment contributes to higher water density and maintains stable layering. Heat transfer occurs mainly through slow movement of large water masses over long distances. Chemical processes proceed at steady and predictable rates. Under these constant conditions, such thermal stability is highly characteristic of much of the deep ocean interior. Bristlemouth fish are known for their efficient feeding strategies in these low-energy environments. Their behavior focuses on capturing small, drifting prey with minimal expenditure of effort or energy. Energy intake is balanced extremely carefully with metabolic needs due to the limited food supply available. Physiological adaptations support sustained function in the cold and high-pressure water conditions. Population numbers can be substantial relative to the available resources because of this remarkable efficiency. Their presence illustrates clearly how energy conservation supports persistence in deep habitats. The example reflects a broader pattern of economical resource use among mid-depth organisms throughout the ocean.